This is part of a human-robot interaction study. Thank you for participating. Remember to be smart with electricity. Water and electricity do not mix. Electricity flow is very similar to water flowing in pipes. The three important terms to know are voltage, current, and resistance. Voltage is like the amount of water pressure in your pipes. The more voltage, the larger the difference in charge between 2 points in a circuit. Current is the volume of electricity passing through a wire per unit of time. You can think of current just like currents in a stream. The larger the current, the larger the amount of charge moving through a wire. Lastly, we can relate resistance to the diameter of a pipe. A resistor limits the movement of electricity in a circuit. In our pipe analogy, a thin pipe is a resistor because it only allows a small amount of water to move. The most important equation to know when working with circuits is Ohm's law. Ohm's law states that voltage V is equal to current I multiplied by resistance R. Or in other words, V equals I times R. We can rearrange the equation in 3 ways to help us solve for any of the 3 values. There are 2 main ways of combining resistors, in parallel and in series. In the next part of the lecture, we will cover these 2 combinations. As discussed previously, resistors impede the flow of current. It is easier to solve a circuit with a single equivalent resistance than with many resistors. In this presentation, I will use RS for series circuit and RP for parallel circuit. Resistors are wired in series when there is the same electric current passing through each device. For example, when you plug your Christmas lights into an extension cord, then into the wall, that is considered a series circuit. Notice when one of the bulbs goes out in the Christmas lights, all of the rest of the bulbs go out. This is because you've broken the chain or the series. Series circuits are the simplest kind of circuits. When you add resistors in series, it's simple addition. In this example, we can combine 6 ohms and 3 ohms to get 9 ohms for the equivalent resistance. Parallel wiring, as shown above, means that the same voltage is applied across each resistor. This means that the resistors in each branch act as if the other branch does not exist. To find the current through the resistor, simply ignore the other branch and use the voltage across the resistor and the resistance of the resistor to find the current. Going back to the plumbing analogy, we can make an equivalent circuit by making the pipe larger. In the illustration above, the right pipe's cross-sectional area is the sum of the cross-sectional areas of the 2 pipes on the left. Resistance essentially describes the inverse of 1 divided by the cross-sectional area of a wire in a circuit. Finding the equivalent resistance for 2 parallel resistors is easy. Since we know that current is like the flow of water, we can say that the amount leaving any point equals the amount entering. Therefore, if we say that in the middle of the diagram, the battery supplying current that flows up the left side, the sum of the currents through the resistors must be equal to that. Therefore, I sub B equals I sub 1 plus I sub 2. Adding more resistors in series is like placing a smaller pipe into the branch and will increase the resistance and decrease the current. Adding another resistor in parallel acts as a pressure release valve. It decreases the resistance while increasing the total current. The next row is talking about the resistance of the whole network as compared to a single resistor. The resistance of resistors in series is greater than the resistance of any individual resistor in the network. The resistance of resistors in parallel is less than the individual resistor with the smallest resistance. The last row talks about what happens when a resistor is removed, leaving an opening in the circuit. If one is removed from the series circuit, the current flow stops. This is why one bad bulb in a string of older Christmas lights makes the whole string go dead. Removing a resistor from a parallel network will stop current through that branch, but the current through the other branches will continue. This is why removing a light bulb at home doesn't make the entire house go dark. Simplifying a resistive network is a repetition of combining series and parallel resistors. Diagram A shows that the 250 ohm 220 ohm are in series. So an equivalent resistor would be one where we add the resistance together, giving us a total of 470 ohms. Diagram B shows that the 180 ohm and the 470 ohm resistors are parallel. To find the equivalent resistance, we divide 1 by each of them to find their inverses. We then add their inverses together, and we inverse that total to find the equivalent resistance. The final resistance equals 130 ohms. Diagram C identifies the 110 ohm and the 130 ohm resistor as being in series. We can add these resistances together to find the equivalent resistance of 240 ohms.
Pass it down.
And remember, resistance is futile.
Oh.
You will now be taking a quiz about the content that was learned. Do not worry, it has no influence on whether or not you will get refreshments. The quiz is two-sided, and we only ask that you answer it to the best of your abilities. Keep in mind that the test is two-sided and that the questions will not be answered except under special circumstances. For